So, without further ado, I'd like to present Don't Trust, Verify by Patrick O'Doherty.
Right, good afternoon, everybody. Thank you so much for coming to this talk. I'm really excited to be back at BSides after so many years and to share with you a story from my last year, a little bit of bug discovery. So I guess to jump in, who am I? I'm Patrick O'Doherty. I'm a software security engineer. I've been knocking around startups in the Bay Area for about a decade. I'm currently a member of the Tailscale security team, and away from the computer when I'm not getting sad at the keyboard, I'm often found wandering around San Francisco with a camera. This is a rare example of me on the other side of the lens from last year. So what is Gorilla CSRF, the library that we're going to be talking about today? So it's a Go library that is a HTTP middleware that is intended to wrap your existing HTTP application with a CSRF protection. And we'll get into what CSRF is in a second. But this is an example of what it would look like to use this middleware in your application. We need it. We instantiate a copy of it. We feed it a server-side secret that's going to be used to generate secure cryptographic random tokens. We take our existing application, we wrap it in this middleware, and then we expose it to the outside world. So what is CSRF? It stands for Cross-Site Request Forgery. And this is, in fact, one of the older forms of vulnerability that exists on the web. And it's essentially an attack where an attacker tricks a victim and their browser into making requests on their behalf. So it's helpful to consider the problem from the perspective of an attacker. They know of a website, bank.com, and a money transfer form, and they want to make requests to that form, to that endpoint, impersonating Alice. But they don't have Alice's credentials, and they don't have Alice's cookie to identify. So their trick is that or their solution is that they trick Alice's browser into making that request on their behalf. And usually this is accomplished by serving Alice, serving the victim, a malicious form that they think is pointed somewhere, maybe upvoting a comment on Reddit, but is in fact pointing to this money transfer endpoint. And so, excuse me. So one of the common patterns in defense against this is known as the double submit pattern, and it works where the server, bank.com, for each new visitor, it generates a random secure value known only to the server and to this user, and it sets that value as a token, and it also includes that value as a form hidden input for every form that is rendered for the user when they visit a page. And then subsequently, for every submission, for every post request, the server requires that the client send a valid and matching cookie and form input value. And if either of those two things aren't present, or if they don't match, then the request is rejected. And so this is how the double submit name comes to be. Two places where the same bit of information is relayed. And so if we return to our previous example, even if attack.com can serve Alice a form that points to bank.com, it doesn't have the ability to send Alice a token or a CSRF cookie that will be valid for bank.com. And so this form submission will be sent with only one of these two halves. Even if they're able to submit or interpolate the form value, it won't have a matching cookie, and so the request will be rejected. That sounds all well and good, CSRF protection, but unfortunately it's not complete. Double submit tokens on their own are not enough. One thing in particular that we need to consider is what happens if an attacker manages to launch their attack from an origin that has what's known as a same site relationship with our application. And the two ways that they could do this are they could perform a HTTP plaintext machine in the middle attack against your origin, and any cookies they set here will be happily sent to your secure destination. It's the inverse behavior that's not allowed. Or they could attack a related website. So it's pretty common for, maybe you have bank.com, but there's events.bank.com, which is a little bit more loosey-goosey with its security, and you can launch a cross-site request forgery attack from there. And here, any cookies that events.bank.com sets on the common site domain that they share between them, those will be valid. Those will be sent to the onward destination. And so many frameworks, Django, Ruby on Rails, in addition to the double submit token pattern, they also have this origin or referrer header check. This is a flowchart that I made of the Django frameworks code when I was trying to understand how this all worked. And I should note that the double submit pattern is just like the yellow box in here. It's, there's a lot of other decision points along the way in an effective CSRF middleware. And the Go library that I'm going to talk about today, Gorilla CSRF, it is inspired by this implementation. It does something similar. So, every story starts somewhere, and this one starts with an email. One of the responsibilities that we have on my team is responding to all the customer questions and interrogatives that we get. I would say that one of the benefits of being at a security product company is that the questions are usually pretty high caliber, or they can be. And sometimes they take a little bit of research and time to dig in and answer fully, and this was definitely one of those days. And so the question was asked, what would happen if an attacker managed to gain a cross-site scripting foothold on either our marketing site or a related domain? And would they be able to use this to perform a cross-site request forgery attack against login.tailscale.com? This is the control plane, the sensitive application where people log in and administer their tailnets, invite new users, add new machines, all of that stuff. So definitely something that we want to protect, and definitely an answer that we want to understand. And I'll put up my hand here and say that my first answer was like flat wrong. I completely just tripped over my shoelaces in responding to this customer. I misremembered how browsers and cookies work entirely. And I gave a very unsatisfying answer, like really ate my hat. And rather than do that again and flub through a second round of documentation, I decided to build a demo to just like see what would happen if you performed this hypothetical cross-site request forgery attack. What would this work like? I'll leave this up if people want to scan. This demo is live today. You can visit it. The source code is available on GitHub. And I'll walk through just the theory of how it works. So this demo application presents two origins. One is the one that we're going to attack, and the second is one that we're going to launch the attack from. It's maybe a compromised marketing website, something like that. And it's important to note that they share this top-level site, this example.test domain. And when the victim visits the phishing website, underneath the hood, it scrapes the target origin for a valid combination CSRF cookie and form value, and then it uses those to render a phishing page back to the user. And it also manages to set a cookie on the common example.test domain that they both share. And importantly, it fixates the cookie with a path that exactly matches the form that they're hoping to attack. And this is important because it takes advantage of two peculiarities of how browsers will send cookies, how they'll choose to order cookies when they're sending to their target destination. And the first is that they'll choose path specificity first over domain specificity. So it's perfectly fine here to fixate on this more narrow form path, and that will clobber any token that was set by a previous CSRF framework. So a lot of CSRF frameworks, they set their token to have a path of just a bare slash, and they do this so that the cookie is sent accompanying all requests to the origin, so it matches every request. But this does leave the potential for us to fixate with our own more specific path, and then it's sent first. And this is in preference of any domain specificity. And then the last thing to note is that this takes advantage of a weakness in the Gorilla library, which is that the Gorilla library generates tokens that are not bound to any user identity. So the server can't distinguish between a set of values that were issued to Alice, to Bob, or to Mallory. And so we don't actually need to guess or know Alice's token, we just need to substitute our own. And so this demo sets all of that up. But even still, I expected it to be rejected because I expected the same origin policy within Gorilla to kick in. And lo and behold, this is what I saw in response. And I'll admit I was pretty stumped. I stepped away and I really thought that I was the problem for a while. It's not uncommon for the error to exist between the keyboard and the chair when I'm involved. But after a while, after some digging, I really was convinced that there's something here. And so I began to dig in, why is my request passing when the library tells me it should be failing? There are even unit tests here that have been passing since the library was committed that specifically address this use case. So what's up? And if we dig in, we can see that Gorilla, it does have this same origin policy code that I spoke about. But curiously, it only runs when it considers that the request is being served over HTTPS. And it determines this by inspecting the URL scheme in the URL that is parsed by the server. And so the question becomes, where does this data come from? Where does this request URL scheme property get specified? And here we can look to the Go documentation, which is very helpful. And if you're a Go developer and you're not frequenting the Go documentation, you're missing out because it changes frequently with updates to the language. And I often find myself forgetting bits of it that are awesome and that I can use. And one thing to note with Go's standard library is that the HTTP library in Go is used to create both servers and clients, and the HTTP request object in the library is shared between them. And so when you're writing your application, you have to remember which mode you're in, and you have to remember which rules are necessary to uphold to make sure that you're effectively holding the request object correctly. And if we scrutinize this documentation, actually all of the information that we need is here. It says, for server requests, sorry, I have to see my own slides. The URL is parsed from the URI supplied on the request line. And for most requests, fields other than path and raw query will be empty. And if we click through to the HTTP RFC, it gives an example of what this is going to look like in practice. It'll say that most clients are going to give us this request target that is just an absolute path that has no scheme or host information. And so the question becomes, where does this data come from? It's not given to us by anybody, but yet it is being operated on in the test suite. Unfortunately, the answer can be found in a bug in Go's standard library and a sort of mishandling of the standard library within Gorilla. So the Gorilla test suite uses a standard library helper function in Go called HTTP test new request. And this function generates request fixtures that are passed through your unit tests for you to make assertions over them. And it takes as its second argument a string that can be either a path or a URL. And if you send it a full URL, it will parse that, and it will populate as many of the request URL struct fields as it can based on what it sees in the URL. The problem is, if you do this in your test suite, you will be returned a request object that's like a Franken request. That's unlike any request that you will ever see in production. And so your unit tests will happily pass green. The branches that you want to have coverage for are green. It's great, but none of this is ever going to run in production. And so, to recap, the origin checks for this library only run when the request URL scheme is set to HTTPS, but in fact, this is never populated in production, and so this code has been inert, and it never actually did anything. So the library was CSRF, it was just RF. There was no CS. And so I think this is like a perfect example of something that friends of mine will hear me harp on about a lot. I love to consume accident investigation or safety material from related fields. And the Swiss cheese accident model, as it was popularized by James Reason of the University of Manchester, says that in a human system, no one layer of safety is sufficient, and we need to compose multiple in succession in the hopes that they're mutual, overlapping, protective layers will form such that no accident can fall through all of them. But here, unfortunately, we have the opposite. Mutual deficiencies line up to allow for this bug to happen. We have the lack of identity binding on the CSRF tokens as they're issued. We have this subtle behavior in the test suite. And then also the fact that this behavior only exists in production and that a lot of people develop, with a plain text HTTP environment, and then they deploy in production, and so they don't see this, they don't try it. And so this lines up to allow for this CSRF vulnerability to exist for as long as a decade. So just in terms of timeline, we discovered this at the end of last year, and we sent a patch upstream to the Gorilla project, and this code is now available in the most recent 173 release. So if you run a Go code base and you have like other websites that you operate adjacent to it, I would highly recommend updating, worthwhile. So that's Gorilla. But taking a step back and beyond fixing one bug in one library, this CSRF problem is a pain, and it's kind of plagued us for 20 years, 25 years. Is it possible that web browser standards have evolved to make this suck less? Mercifully, the answer is yes. And the answer comes in this more recent technology called fetch metadata request headers. And these are a set of headers that browsers now send accompanying all requests to what they consider to be trustworthy origin, so anything served over HTTPS. And they explicitly signal to the server what the client believes to be the context of the request that's being made, whether it's cross-site, whether the data is going to be interpreted as a document or a script, what have you. And so previously, where we had to infer all of this, the clients now just tell us, and we can make these confident decisions about whether the request should be served just from these headers alone. So this is an example of what that would look like when site.example includes a same origin fetch request to foo.json. And so the client here can understand that site.example and the requested resource have a same origin relationship and explicitly tell us, and we can accept that. That's all great. But conversely, if we had a malicious origin, if we had evil.example try to include that same resource, the client can discern that the two origins have a cross-site relationship. They don't have any relationship to each other and will tell us, and the server can simply reject us. I am in love with the simplicity of this solution. Where previously we had to infer this and there was a lot of like at a distance, it's now just explicit. And this is how it looks in practice. So, you know, it's a much simpler thing to implement. There's no server-side credential to manage in terms of token generation. If you want to go even further and block GET requests to prevent leaking of resources cross-origin, or, you know, prevent cache timing attacks, you can do that too very simply. Yeah, and there's no potential for this to drift. If, for example, your web application finds itself sometimes behind a reverse proxy that changes the origin from the perspective of the client, but the app doesn't know that. Sometimes you can have CSRF false positives. This is a current pain in my life because we ship a client that sometimes people embed in other contexts. And so this is just much simpler. The client will tell you what it believes its relationship to the requested resource is, and you can take that at face value. So these were made available in, or first introduced in 2019, but they've become broadly available in all standard browser revisions as of 2023, so they're now generally available. We are currently running some instrumentation to evaluate whether we can replace double submit cookie protections with this middleware instead at Tailscale, and it's looking imminent. We see like 99.98% compliance, like a real like rounding error of non-compliant, mostly old Safari Grumble releases that are catching up. But yeah, it's the new technology, and we're going to use it. So what can we take away from all of this? The first is, you know, unit tests are just the beginning. We should really kick the tires of our code. You know, it can be helpful here to create small experiments that, you know, demonstrate the integrity of the security controls that we rely on, so that when we poke them, we don't find out that they're paper thin. You know, we should validate the assumptions on the differences between our test and development and production environments. Here, there was only one bit of information that differed, but it was crucially the bit of information that mattered to make this middleware effective. Again, you know, like we should really just do the experiments and empirically measure rather than make assumptions. These new fetch metadata request headers are awesome, and we should all use them. But they're also, you know, representative of the fact that HTTP, the OWASP top 10, these are not concepts that are, you know, set in concrete. They evolve over time. I'm actually a little bit disappointed that this technology was available for, you know, so many years. I didn't know about it. I watched these headers go by in various logs, and I just like, I wonder who they are for. But they're really cool, and so I'm going to take on myself to try and be a little bit more, you know, up to date on the professional standards as they are. You know, there's good stuff in here for us to bring to bear for the benefit of our users. And yeah, with that, that's me. I realize I managed to get through this. This is the fastest run I've done by like many minutes. So yeah, I'm going to turn it over for questions and say thank you so much to BSides for having me, for all the staff that puts this on and makes it possible, and for you for your time and attention.
Yes, thank you, Patrick. That really was a lightning round. You have at least, you've got 10 minutes now, which we could fully put in for Q&A. So as a reminder, the way that we do Q&A, as I mentioned before, is through Slido. That's sli.do is the fastest way to get to that website, and the conference code BSides, plural, SF 2025. We are in Theater 15 according to the schedule. So just select Theater 15 and submit your questions there. I'm going to be reading out the most popular questions. You can upvote questions if you see them and they are exactly what you want to ask. That helps us prioritize things. Because we have so much time, I'm certain we're going to have hopefully lots of questions. So here, let's take a look at them. All right, we've got several pouring in. So in Kubernetes, a lot of add-ons are there, which are from open source container images from OPN source registry. I want to make certain this is for the right. Does this seem like a relevant question? How do you manage open source container images?
I mean, I could speak to that, but I don't.
Yeah, that looks pretty strange. So we're going to save that one. How about this one? That seems relevant. What would you use this new method in addition to double submit?
My hope would be to replace double submit with this entirely, because really, like, the most important bit of double submit is the origin. The double submit, I think the cookie portion of it is actually not as useful. I think we kind of combined the cookie method of relaying information and the fact that we can only set cookies for same sites with this origin header checking. And in fact, I think if we could just do better origin header checking, we wouldn't need the cookie thing. And it means there's one fewer credentials to manage. You can deploy this without configuration. So my hope is that it can entirely replace it, because I think some of the even some of the more secure CSRF APIs, they're easy to make brittle by generating tokens that are too narrow for the scope that you're authenticating. So I much prefer this, just because it gets rid of a whole bunch of usability issues that I previously didn't consider, but that with the open source viewpoints that we have and seeing so many wide deployments, they definitely add up to some amount of pain that could be just completely done away with.
So this next one is popular. Tell me what resources you look at for accident investigation hobbying.
Oh, I read anything that, US Chemical Safety Board, YouTube videos. Definitely there's some people in here who watch those. Those are great. Anything, that the US Air Force or the Navy or various organizations around the world will release, because if you think about it, they're just, they're human-computer interface problems. It's just that they're giant, billion-dollar hunking pieces of metal that have computers in them, and ours are just little laptops. But they're exactly the same thing of human psychology, of the computers conditioning us to think that they're always reliable, and then they have catastrophic failures, and those patterns exist both in our domain but also in these domains, and seeing how they make themselves resilient to these catastrophic failures is highly educational.
Do you think this can get into the Go standard library? There seem to be a lot of important checks like this and DNS rebinding that keeps getting longer and longer for people trying to use Go.
I would love to see this in the Go standard library. Yeah, I think this is a missing stair in the fact that you could write a Go application, use all the Go standard library stuff, and then have this as a missing thing. So yeah, there is some hope. I would like to see it in the Go standard library. I think there was previously a proposal to take the extended Go standard library, the x/space has a XSRF token API for generating the cryptographic tokens, but it doesn't have a HTTP middleware for integrating it into your app. There was previously a proposal to bring that into the standard library, but it kind of stalled out for a lot of reasons to do with all of the usability concerns that I spoke about here. I think this solution, because it is just that much simpler to implement, has a better chance of being the thing that lands in the Go standard library. So I have my fingers crossed, but I'm not a committer to Go, which is can't make it happen.
And then just to clarify, you haven't shown any issue with the Go standard library itself, right? This is for a particular framework called Gorilla?
So there's two bugs here. One is the Go standard library HTTP test new request helper that had confusing behavior that should be clarified, because effectively there's no way to easily use it to generate test objects that are like what you are going to experience in production. So it's effectively setting you up for failure. So there is an open issue in the Go tracker to fix that and make it possible to not fall into this trap of writing sort of tests that don't actually represent production behavior. And then separately, there was the bug that it enabled in Gorilla, and that has been solved, yeah.
We still have 5 minutes here, so keep piling these in. We're doing really good. Do you have any ideas about how we should in general learn about these types of new security tech, like these headers? Good place to go or place to start reading?
Yeah, apart from reading MDN every now and again, I am looking for good answers to this myself. Like I'm going to write about this publicly in blog, and I'm going to contribute my bit to the amount of information out there. I do follow newsletters as well, and that's like I try and keep my ear to the ground and see what's coming up. But yeah, I haven't one good answer for where this new information comes from.
So this one is multi-part. So the first really kind of depends on whether you have looked at the docs for HTTP test. Have you looked at the?
I have looked, not in the last week, but I have read them.
All right. So it asks, do you think the ergonomics of that function are surprising and that similar bugs might hide in other code bases that use it to test prod HTTP implementations?
I would not be surprised. I did write a Go vet that looked for the specific behavior in Gorilla that was problematic, which was making a direct comparison against properties in the URL that you couldn't guarantee were that were set in production. And so I have a Go vet that you can, I can add it to the appendix and I'll link it out to people. You can run this over your code base to see if you're doing the problematic behavior. I tried to run a GitHub search to identify projects, and there seem to be others, so I'm pretty confident that there are other projects that have either emulated Gorilla, their implementation of CSRF, or have made other sort of false steps with using request properties that aren't actually there in production. Yeah, there's probably more research to be done here, so I'd encourage it.
In that vein, do you think there's anything that Go should do differently to prevent these kinds of issues in the future? Quite open-ended.
I mean, my scorchiest take is that HTTP requests created this because it's dual purpose. Dual purpose APIs can induce misuse, and I think my ideal world, having come from some languages with more aggressive type systems, I would like to bring, type system design, static analysis, other things to bear to make this misuse resistant. I think, if you make something possible, over time, chances are people are going to do that thing. And so I view this sort of like as a harm reduction API design. Like if you make it possible, people are going to miswire it. So just don't make it possible.
So we're out of questions on Slido, but I know sometimes people are shy typing and paradoxically great at speaking out loud. So as one of the privileges to extend you here in Theater 14, is anybody want to ask a question? Just make it short. Raise your hand. I'll try to listen to it, and I'm going to repeat it for the stream, and then we'll have it. But if not, go ahead.
Safety board also does great videos. Not as good as US Chemical Safety, but.
All right, so there was just a suggestion of the Canada BC Safety Board, which is alike, if you've ever seen the US Chemical Safety Board's videos, is another great accident investigation tool, resource. Is that your? Yes? Okay.
Cool, safety sickos rise up.
All right, well, Patrick has volunteered, as many speakers do, a really amazing resource. You can talk to him up on in floor 4 in the vendor area. He promises also to stay for all the various parties. And so I really would like to thank you, Patrick. And thank you all for attending BSides here. We have one last one. Okay, you ready for a star round? What suggestions do you have for a beginner to start identifying security bugs?
I mean, just keep asking questions and really there's a humility to just letting yourself be ignorant about something and experience it for the first time. I don't have any credentials in this. There's no reason that I can be here and nobody else can. So just giving yourself permission to be silly about something is opening the door to having a fresh perspective on it.